All right, welcome back, everybody, to the Additive Snack Podcast. This time in a bit of a different format, which is for the first time live at a conference. We've never done this before, but I'm super excited to have multiple guests here at the RAPID TCT show in Detroit. And our first guest is the great Dr. Andreas Vlahinos. Andreas is one of the masterminds of design in additive manufacturing. If you've seen this part here, one of the most awarded additive parts and heat exchangers in the industry, that is Andreas's work. He has been in the industry for a long time. And as I said, is one of the thought leaders in that space. He gave a few talks already today. So this is number 3 of your engagements. A lot to talk about at the show. So today we'll talk about, of course, design for additive manufacturing. We'll talk about the different approaches, industries, bit of also Andreas's story into the industry. And therefore, I'm really excited to have Andreas here with us today. So Andreas, welcome to Additive Snack.
Thank you very much for inviting me.
So Andreas, as I just mentioned, to make you feel very humble, you've been in the industry for quite some time. You are one of the most decorated designers in the industry. So tell me a little bit about how design for additive manufacturing has changed over the past 3 to 4 years, because I think a lot has happened.
Yes, we need to go a little bit back before 3 to 4 years.
Okay,
yes.
Let's go all the way back.
Once upon a time,
Yes.
a long time ago, when the parametric CAD systems were involved, we were able to make designs that we couldn't manufacture.
Correct.
Like in internal holes and cavities and stuff like that. About, I don't know, half a dozen years ago, we fell behind with the progress in additive manufacturing, in powders, machines, scanning techniques, etc. We were able to build parts we couldn't design. So it was an evolution in the computer-aided design area where we had companies and startups start to give us the ability to design, for example, lattice structures.
Sure.
I was introduced to gyroids in the 80s, and I said, wow,
Really?
what an amazing structure. And we spent the master thesis on doing one unit cell, and we were really proud of it.
Yeah.
But we couldn't do anything. We couldn't manufacture it. We couldn't build it in time. Now, the last 6 years, a lot of CAD systems like, Creo and Enthop and etc. give us the ability to design the structures.
Okay.
Now, at that time, we were able to design, let's say, a gyroid and specify the thing,
Yeah.
which was exciting to see it, complex, you can make it in additive. But we couldn't analyze it, and we couldn't do design exploration. The user specified the thing. Now, to answer your question, over the last 3 years, there is enormous progress in simulation-driven design.
Okay.
Now we can do an FEA simulation of a solid part, store the results in an ASCII format, and then bring the gyroid and say, okay, proportional the thickness based on the residual stress or on the von Mises stress or the maximum temperature and etc. So one of the big improvements, enhancements in design for additive is simulation-driven design.
Okay. Good.
The second, also there is a major issue we need to overcome with these new tools. These new tools are either implicit or voxel-based.
Okay.
And over the last 100 years, we do simulation based on BRAF geometry. So we save something in the neutral format like step or parasolid. We bring to the simulation and we do something about it. Now we can do that. You can step out or parasolid out an implicit or voxel geometry. So it was a big gap between design and simulation. Now, if you ask me what happened over the last 2 years, then what exciting thing happens, simulation technology start using voxels instead of traditional finite elements. So the interoperability has improved. So we
Okay.
can do real-time simulation within the CAD environment.
Okay.
And you say, oh, big deal. It is big deal because we used to have hidden line removal mode, and then in the CAD, and then wireframe, and then shaded with edges. Now we have a fifth mode, which is simulation results at the same time as the designs. So if you see a high stress there, you double-click the fillet and make it bigger, and you find the next hard pain point, and you go change that. So big difference with the real-time simulation. So I can go more and more on these things if you want, but
Yeah. Well, maybe let's double click on that. Because I think not every designer or engineer out there has been a part of that journey over the past 2 to 3 years. But I think some people even feel a bit left behind. Can you maybe give us a quick overview of differentiation of the different design tools that exist today, from implicit to more traditional CAD modeling, and when you would apply each model, right? Because I'm guessing there's a space for everything.
true.
And not everything needs to be a simulation-driven design process.
True. You're right. The workforce have fallen behind.
Yeah.
There are a few reasons for that. First, the accelerated technology improvements within these teams. Every 6 months with every new release,
It's hard to keep
of
up.
additive manufacturing.
Yeah.
The second reason is the academia has not caught up with these tools. So the professors are really behind on the knowledge of these tools. So it's hard for them to teach them at the university environment. First, they don't know, or they didn't have access to tools. And the third reason is the academic system is based on accreditation. So in order to bring accredited courses, they need to go through a big bureaucratic process. And those things move much faster than the traditional bureaucratic courses of academia. So right now we graduate engineers and they don't know that.
Yeah.
There are a few exceptions like Vermont State University, Colorado State University, which I taught design for additive manufacturing courses, and it's enlightening. So what the industry does now, does custom training in-house. Like I trained about 180 engineers at Lockheed Martin last year on design for additive.
Wow. Okay.
And they're ecstatic because they say, oh, I didn't know we have this tool under this menu in my desk. Okay, so
It was there all along.
it's all there. Yeah, so they don't know what is there,
Yeah.
Now, with respect to the tools, I use two of them. One is PTC Creo, which have integrated voxel-based design and Creo simulation live, which they're very easy to use, but also they have limitations.
Okay.
Like I can do Boolean operations between voxels, And I use another tool called Nthop, which is from anthropology, which is implicit modeler. Now, implicit modelers are extremely powerful. They can do very large lattice structures from very fine unit cells, plethora of unit cells from TPMS to beams to plates and etc. incredibly fast. And they have capabilities we can find in other tools, like blend the gyroid with a cell, stuff like that, or do a Boolean operation on a gyroid, like shell out the gyroid so you can have a double wall inside, so you can do very creative things. So this is the progress in these tools. Nthop is powerful. He struggles with interoperability, although there are some efforts for vendors like Magix and EOSprint to read implicit geometry.
Yeah.
But the interoperability is a serious issue. Usability is a serious issue because there are a lot of new patterns and blocks and things which they don't streamline. But they're working on that. We're pretty excited on the progress of these things.
Yeah, they continuously, and they've come a long way too, right? Like you just mentioned.
Amazing, yeah.
Let's talk a little bit about projects, right? This is the first time I met you years ago when you were working with our team and PTC on this heat exchanger. What's been one of your most exciting projects in the past few years that you're really proud of, that really got you excited, and that was something that you might be able to share?
Yeah, we do heat exchangers and generative design brackets all the time. And it's very rewarding to see a heat exchanger which performs much better than the one before, and it's lighter and stronger. This is exciting. But what was most exciting when you impact human life. Like I think about 2 years ago, a young lady called and said, I have cancer on my femur. I need an implant in a week.
Wow.
I said, why me? Your kids is like this, so you should be able to do it and stuff like that. Anyway, to make the long story short, I had to learn quickly how to import the ICOM data
From a CAD scan.
From the CAD scan. Generate an STL, generate a solid after that, slice it with the conscience, virtually remove that part, put an implant, incorporate the brackets for the implant, do gradient-based thickness on the gyroid, talk to the doctors, what do you want for porosity so we can do osseous integration?
Yeah.
And then they say, oh, by the way, we need to put a big nail through. You need to make sure you have the fold there. So all these things had to happen very fast. We did it. They printed. They did the operation. And in 2 weeks, the young lady walked without limping. And that was more than once. And I didn't get paid for it. But anyway, because it was just,
Wow.
labor of love to be able to. So that was one of the most exciting recent projects.
Wow. So you became a medical device designer over 10 days then, huh?
No, not quite. I struggle a lot to go from the ICOM to STL. After that, it was trivial because we do that for defense and aerospace and defense.
Yeah.
And one of the improvements, for example, in the CAD system is we can take an STL and string wrap it with regular geometry. They call it subdivision and surface modeling. So we can have a CAD model, solid CAD model. We can slice it, dice it, infill it with gyroid, sell it out, whatever. So the power after that point, it was already there, and I was very familiar. Okay. But it's very rewarding to impact somebody's life.
Yeah, sure.
They were planning to amputate because the cancer will spread, so it had to be fast. So that's the...
That was 2 years ago?
It was, about 2 years ago.
And she's still...
Oh, yeah, she's
still
great.
good?
She's in great shape. Yeah.
Okay. That's awesome.
And also it helps us foster innovation.
Yeah.
I hate to say that, but the doctors are not very aggressive and open to innovation.
No, they need to be conservative.
Very
right?
conservative. Yeah, I told them, can I make it 2 parts so I can put a screw so we can turn it outside so as it grows, the bone grows.
Oh.
And they didn't want to do that. Because it wasn't that before and they were in the area and stuff like that.
Yeah.
But it can foster innovation. Or they put a big nail from the top of the femur bone all the way down. I said, can I put a hinge there so we can make the implant with hinge to go in? You don't need that nail. Oh, no, that's never done before. Well, so what? So anyway, but there is a lot of room for innovation in this.
I hope we have some medical device manufacturers listening. Call up Andreas. Okay, let me dive a bit deeper into heat exchangers. I think it's a huge topic right now. Obviously, additive and thermal management are an awesome match. We see heat exchangers applied in various industries, right? From space to aerospace to the semiconductor and data center space, yada, yada, yada. Take us a bit through your process. So if you have somebody come in that has a case for additive in a heat exchanger environment, how do you get to a final application? How do you approach that process?
That's a great question. We have to go through several stages. The first stage is, could I print it? Will it fit in the envelope?
Okay.
Do I have the material? Do I have access to the printers? And etc. So the first is, could I? The second question is, should I? Does it make financial sense?
Sure. Okay.
To make that simple heat exchanger instead of tube and cell or plates added.
Yeah.
If this costs $10,000 in the other costs, let's say $4,000. Well, what happens, the customer says, the $4,000, I need to change it every 6 months because it's brazed and it fatigues and I need to put another.
Okay.
What's the fatigue life of that? That's infinite fatigue life. And if you put the right adapters, you can put it exactly in the same spot.
Yeah.
So we have to do this often. So could I, should I, do I have the available materials? And then we go through a special process to see if it's feasible to do that.
Yeah.
The feasibility, like if I need, what performance do I need?
Sure.
If I don't beat it twice, the performance, I'm on the video. If
Well, that's why we're live, right?
yeah,
On the
it's
show.
like,
Yeah.
so if we were able to beat the performance, even if it costs a little bit more, but the performance size weight is better, performance like fatigue life,
Yeah.
the helicopter, you don't need to change it every,
Yeah, lower
5,000.
maintenance.
Yes.
Yeah. There's
long term, then it's worth it. And the other point is, do we have the ability to prepare the data so we can print on demand on location?
okay.
So we can have a digital library of EOS print files so we're ready to print instead of, okay, here's the CAD model. What's the print orientation? What are the supports? Where should I add material for machining? Where should I add material for surface finishing? Should I plug the holes and drill them afterwards? There's so many other things in post-processing you consider.
Yeah.
So the big deal nowadays is to create a digital twin of the as design model. So we have two models, as design and as print. And both are stored in the PLM system. So when you're ready to print, the printed model comes down and it contains the orientation, the supports,
A full technical data package.
all the technical data package need to contain more than just as design.
Yeah.
So
Okay.
that's the big lesson learned there.
So you really start with a very long feasibility study of why should I even open up PTC or NTOP, right?
Yeah.
Which is comparative technologies in the conventional space, cost, full supply chain, including end-of-life considerations.
Correct. Yeah, you need to consider this thing to convince the customer it's worth to invest more now.
Yeah,
Because
Yeah.
in long term, they have one heat exchanger of 10 over the 10 years.
sure.
So in some cases, it makes sense. Some other cases, it doesn't make sense.
That's additive.
If
Yeah.
it's like a sheet metal part or, a very simple, thick, chunky part,
Yeah.
then
Yeah.
you
Yeah.
don't need to do that. So you need to find the value proposition. It needs to be a compelling reason for the customer to come and say, yes, I want this.
Yeah, and that's a great service also to the industry, right? We see companies get into additive that sometimes shouldn't, or at least with that application, right?
Yes.
Because it's going down the wrong path. But let's assume we have a really interesting case for a heat exchanger. How do you approach the design phase? Right? Because there's a lot to consider. There's one thing you just mentioned, which is post processing.
Yeah.
But do you start? How do you
How do I
approach it?
start design
Yeah.
for heat exchangers?
Yes.
Oh,
Yeah.
I can tell you. First, you identify where the inlets and outlets need to be.
Okay.
Then we put a chunky volume around it, just
Okay.
a big chunky volume. And then we run the CFD
Okay.
on a big volume.
And the CFD based on certain parameters already.
In inlet and outlet, temperature and flow rate.
We have flow rate, pressure, any pressure
No,
drop.
pressure it's
requirements?
0 here and 0 here.
Okay.
And the TPMS structures have usually very low pressure drop. and they're sinusoidal, they're smooth coming up. So we don't run into that as a controlling factor.
Okay.
So we take a big chunk of metal and we run the shifting. And then when you see the flow lines, it guides you where to put material, where to put the heat exchanger.
Okay.
So when there is circulation regions, I don't need to put anything there. So the flow lines give us a profile which we will sweep. We get the basic volume. If that's a reason, for example, this sticks out and the other one sticks out because you went from here to there. So the flow lines guide you. And we can either have automatic way to go from the flow lines to the solid, or we can do a manual. You say, oh, I see, I don't need any material here because it will circle.
Okay.
Then you build a solid volume around that. And the next step is to do what we call conjugate heat transfer. We apply the inlet and outlet flow rates and temperatures, and we find outlet temperatures and pressure drop, and we see the performance. We find something we call the efficiency of the heat exchanger. Efficiency is how much heat potentially you could dump from one side to another, and how much do you really dump. The ratio of how much I really dump over the maximum possible is the efficiency. So we find the efficiency and say, oh man, that's not efficient. Let's do something about it, like make the unit cell size smaller.
Okay.
So we play with the cell size, and then if the pressure drop is very high, we say, do I need this uniform cell? No, I will make in the longitudinal direction bigger cell size and smaller in the other two directions. So we have plenty of parameters to play. So what we do design exploration. In the design exploration is not something you just look and explore. You do because you have parameters you can control, like the unit cell size in the three directions, or gyroid or diamond, or, others, I guess. So we can generate the design of experiment to say, okay, play with these dimensions. So we need the design variables in the range, if it's continuous, and if it's discrete, a list of potential, let's say, unit cells, gyroid, diamond, IPLP, or whatever. So we have this, so the combination can run automatically because this real-time generation tools can compute these things fast. So you have finally a matrix of results.
Yeah.
And you can do, I don't know, we call them parallel plots or Pareto plots. You can do a design exploration and you do scatter plots, let's say pressure drop temperature. And it's a bunch of dots everywhere. Looks like a football, with a bunch of dots. And you can show I want the maximum delta P and the minimum pressure drop. So from that football, I want to be on the top. You call that Pareto front. So we can do design exploration and optimization. So we're not after good designs. We're after great designs.
Okay.
Because we optimized, so we can minimize the weight, meet your performance requirements. And then the next step, which is painful for me, is the manufacturability. You go to the manufacturing guys and say, here's the design, it's great, it has all the performance. And the manufacturing guy says, oh my gosh, how do you want me, let's say if you will print it like that, how do you want to support
now we need
that?
support structures all the way in.
That's
Yeah.
So,
and that's actually my follow-up question, which is, how do you now take the true manufacturing into account in your design? Because there's not just support structures, right? There's different materials. Of course, every material, like, do I do aluminum, or do I do copper, or do I do a stainless steel? Now I can do different wall thicknesses. So how does that all flow into your design process?
We, in the design exploration, we do design of experiments. In the design of experiments, we need the variable, let's say the thickness of the gyroid, but we need to put also the range of volume. So the minimum, so we ask the manufacturing guy, what's the minimum you can print? He says 1 millimeter. Okay, we'll go from 1.1 millimeter to about 2 millimeters. So that's part of the design exploration to do that.
That's awesome.
So we meet the performance, then we go to manufacturing. The manufacturer says, oh, no, we can do this. You need to change that. Or they say, for example, I need to machine threads here. Where do you want me to hold it?
Yeah.
Well, in the global coordinate system. No, where are my datums to do that? So you need to put datums for them to hold it and etc. So you learn the hard way where to go, you know? So it's really not easy
No.
to do that, so to follow the process. And then finally, the final steps. You satisfy the manufacturing guy, you satisfy the performance requirement, you optimize the design. And the big question is, will you have any build failures? I say, wait a minute, let me do manufacturing process simulation. So we do manufacturing process simulation.
Yep.
So we can find the residual stress. We can find the what we call plastic strains. And if the plastic strain is high, say, darn, the residual stress is too high there. Let's look at it together. And you look and say, oh yeah, I have that very thick plate to that thin gyroid. Can we do some transition? Can we do a fillet, the chamfer? Can we reduce that? Can we, if as we go up, we do something very simple. Don't tell anybody. We cut the cross-section of the part and we find the area.
Yeah.
And then we can plot in milliseconds the area versus height. So if you see a jump, say, oh my God, what's going on here? What did we miss here? Oh yeah, a plate comes on the top. Oh darn, do you need that plate flat? Can we make it corrugated?
Yeah.
So can we make it, all the way around with a slope? And then do you want them parallel to itself, or we can raise them a little bit? So as you slice it, you need to have a smooth area transition from one to another. So it doesn't take a rocket scientist to identify this. What it's hard is the manufacturing process simulation, because it's intense computing, but it's an eye-opener before the build failures. For example, oh my gosh, we didn't put enough supports and the support lifted up yet.
Yeah.
Or, oh my gosh, we put too many supports here, we can't even take them out.
It's expensive as a mistake. Yeah.
So, yes. So we need those tools improve it, okay? The TRL level is about 6 to 7 now. They pass the, the chasm,
The chasm.
Yes. So they're getting better. They're getting more usable. And every engineer, before he prints, he needs to do that, especially complex geometry.
Yeah.
If you have an experienced guy, he gets it. He looks at it and says, oh my gosh, what? All of a sudden you go to a very thick plate, and underneath this thing, it will cool off. And then when this guy decides to cool off, it will be too late. It will swing. And the other guy says, wait a minute. So the residual strength will crack. So the last final step is to do what we call manufacturing process simulation to avoid defect.
Okay. I mean, it really also sounds like there is a very strong collaboration between the design team, the manufacturing team, which is not always the same as the post-processing team, right?
Yeah.
Right. And you need to manage that project and all those stakeholders in your design process to ensure you get to a production parts with as little try and error as possible.
Correct. Collaboration is the key to this thing. And we didn't used to have that. Now we have to.
Yeah.
Because otherwise you can print it, you can manufacture it, you can post-process it, you can finish it.
Yeah.
I'll tell you an example. It was embarrassing. It's like we did a waveguide.
Yeah.
For the radar systems. And the waveguides are about 1 millimeter thick. So we designed for 1 millimeter. We print beautifully all the parts. And then we tried to finish the inside. The finishing process was taking about 1 millimeter off. So we had a hole. No, my God. So you really need to collaborate this and find out, if I do this finishing technique, I take so much out of the surface finish. Let's compensate for that. So you can make it, 1.12 or whatever. So there's so many things we still learn to do that. So collaboration is the key between performance requirements, guys, design, simulation, manufacturing, post-processing, and of course, it needs to make economical sense.
Okay, so now we talked about the full design process, and I think it is still complex, right? I mean, let's be real, right? It takes experience and it takes collaboration to get to the final point. But I think also it takes is passion. Right? You need to love what you do, and you need to be able to like dive into that topic and really try to become an expert in it. So what drives your passion? Because every time I see you, you have a smile on your face. You love talking about additive and design for additive.
Yeah, it's really rewarding when you can solve new, unique, and difficult problems for the industry, and you see a heat exchanger performing better. You can see a projectile not vibrating. When you have impact on the final product, it's very exciting.
Yeah.
Especially when the traditional designers don't cut it, or the traditional designer says, we always done it like that. What is this, stupid bracket? There is no way this bracket will be as strong as this.
It's my solid, chunky bracket.
That's right.
Yeah.
It says, sir, we use generative design for this. It's actually stronger than that because it doesn't have a stress concentration there. And the guy, I wouldn't mention the customer, he says, no way, let's test it. And we test. Then we go to the design load, nothing happened. Go 1.5 times the design load, nothing happens. Okay, break it. I want to see the weak point. Sir, there's no weak point. Generative design, everywhere is the same stress. So they load it, and we get fine. And we go there to see what they broke. The pins broke on the belt cut, not the belt cut. And then he got upset. He said, son, although she was older, you over-designed this. You need to go back on the drawing board. Like half an hour ago, this is no way. Yeah. And now, this is too exciting. Let's do it,
That's passion.
So
that's passion.
Those are the rewards.
Yeah.
Yeah. My wife keeps complaining, why you work when you don't need the money? Let's retire. Let's go.
You love it.
It's so much fun.
Yes, you love it.
It is fun.
Yeah. And you love it so much that even a while back, your son followed in your footsteps, right? So he also is a designer. How did you bring him up to become a engineering mind as you? And what was it like to work with your son together?
It's really exciting to have your kids inspire. We inspire them with traditional tools. Help me build this deck, or help me make this bracket, and then they see what you do.
Yeah.
So that you get paid to play in your computer like that, and you spin these models and change them.
Yeah.
So he became a mechanical engineer, and he worked for us for about 8 years. So he learned the pain. The pains are, for example, interoperability. How do I go from the CAD to simulation? How do I go from the simulation to collecting only what I need? Let's say the maximum stress and deflection. I don't care about the simulation. I don't care about the finite element measures. I care of the maximum deformation and the display. Now, can I put an umbrella over that, like an optimization tool? So I can play with my design variables to achieve the outcome or the optimization. As I told you, we don't want good designs. We want great designs.
Okay.
So that's the outcome. So he works now for NTOP for the last 8 years. He have a ball. So when we ski together, we're on the lift together, believe it or not.
You guys talk about AM design.
Yes, we talk about design for additive.
Okay, that's awesome. But it's a testament to your passion, but also really a calling for what you do.
And I was the first 20 years of my career, I was a university professor, and the last 20, I do consult. So you learn freely to share the knowledge with your colleagues, the people they need it, and then that pays off.
Yeah.
Because when they start, they call you, hey, can we solve this problem together?
Yeah.
Can we do a better anyway? Rocket engine, can we do, very exciting stuff. We're living an exciting time. The tools improved a lot. The integration is getting there. It's not quite there yet.
Yeah.
We still need a lot of stuff.
But it's advanced a lot, huh?
Advanced a lot. We
Yeah.
still want more. We want to be able to integrate, for example, topology optimization for generative design to generate smart architected materials. And they're not quite there. We push the vendors. We tell them how we do it today manually so they can automate it so we can get the benefit of automatic generation of food.
Okay. I have one more question for you, and that is, when you've talked a lot about also inspiring and teaching new generation designers, but I think also existing designers. What's your advice to somebody who has been a designer for years, understands conventional manufacturing, is entering additive manufacturing? How do they start to get into the design process for this new technology? How do they reduce the frustration during that process? And how do they ensure that they have the highest rate of success in that process?
That's a very difficult question because some of them, when they're very close to the end of their career, they don't want to touch this.
Yeah.
But education, it's not information, it's inspiration. So you give them a talk and you show them how a great designer, nature, is using lattices, additive, believe it or not, or topology technique. The trees are moving and they have a big fillet on the bottom because they were building it as needed material. The butterfly wings have gyroids, so that's when they have long span and very thin. So the first lecture in my design for additive manufacturing course, that's the only commercial, it talks only about natural structure and how woodpeckers don't get brain damage. They hit enormous impact on the tree and they keep doing it. They have lattices, energy absorbing lattices, in their beaks, the rungs, the mantis shrimp. There are so many amazing examples in nature, which they use lattice structures to do that. So the question is, would it excite you to use this in your design and make them lighter, stronger, higher performing, lower temperature, and etc.? So first, that so you can inspire. The second, you need to give them seeds to start innovating. For example, I'll give one more example and then
they're all good examples.
In their planes, they have a lot of electronic boards. And they generate a lot of heat. But they're so packed together, you can't do anything between. But they're in a rack. We call it the chassis. So try to imagine the chassis looks like cells, and they put all the parts. At the end, they have ribs for cooling. But the board in the middle overheats a lot more than the other. So, okay, let's make the ribs higher. Oh, no, there's something else on the other side. You can make the rib higher. But if we made it from additive manufacturing, we put a cavity inside, close to that hot spot.
Sure.
A cavity, and then where does it go? Try to imagine a cavity there. It goes up to the cool place. And then what do? That's cavity, that's air, that's worse. No, hold on. Put a couple of drops of water and plug it. And now it becomes a heat fight. It goes there, it evaporates, goes up, it gets cool, comes down. So it becomes a heat pipe embedded in the power electronic. So innovation is amazing with the ability of additive. I gave you one example. I can give you about 50 more.
I'm inspired.
Oh my gosh, what we can do now, if you open your mind, the hardest part is the mindset. The last 150 years, we designed the courses at the university environment for subtractive manufacturing. They never heard the word additive. Till recently. And the courses are still the same.
Very true.
Oh my gosh!
Very true.
It's if you go to a traditional university, which they're not progressive on this thing, the courses are the same. You never imagine to embed a heat pipe in a heat exchanger because you couldn't make it.
Yeah.
You know,
Yeah.
we couldn't imagine lightweight a drone wing with lead because we couldn't manufacture it. Now we can design it, we can manufacture it, we can validate it on the digital environment, and then go from digital to physical with 3D printing.
That is a great last sentence for a really good episode. Andreas, it was a
Thank you very
pleasure to have you with us on the show.
Thank you.
I learned a lot. I hope we will have you back on the show and maybe do a bit of a deep dive into one of your projects, if we can. Very educational. Thanks for being here with us today.
Thank you very much for inviting me. Thank you.
And for you out there, if you enjoyed this episode, share it with your network, with your friends, with your colleagues. I'm sure just as inspired as I am, you were, and I think your friends will be as well. If you want to give us a review on your favorite podcast platform, you can give us up to 5 stars. And I will see you next week.